Chapter 24, Gauss's Law. In the previous chapter, we studied Coulomb's law, which tells you the electric force between 2 point charges. And from that, we can calculate the electric field of any charge configuration if we apply the superposition principle. But in reality, if the charge configuration is complicated, for example, a three-dimensional continuous distribution of charge, then we have to resort to a complicated integral in order to find the actual electric field. Is there a way to simplify this process? Well, it turns out, under certain circumstances, we can. And to do so, we have to introduce an alternative, and that is the so-called Gauss's law. Okay, so the first question is, why do we need Gauss's law? It in fact can be derived from Coulomb's law, so it's in principle nothing new. The question, why? And the answer is that with Gauss's law, we have several advantages. One is, we can find the electric field of certain continuous charge distribution with high degree of symmetry. For example, spherical symmetry, say a uniformly charged sphere, or a uniform spherical shell, or cylindrical symmetry, for example, a uniformly charged cylinder, and planar symmetry, for example, an infinitely large uniformly charged plane. Examples like these. A second advantage is the so-called ideal conductors. Those are conductors that can conduct electricity without any resistance. We call them ideal conductors. It turns out, with Gauss's law, you can easily calculate the electric field right outside an ideal conductor, regardless of the shape and size of the conductor itself. And this will apply to arbitrary charge distribution as long as it's an ideal conductor. So, let's see how we can derive Gauss's law and how we might apply it to these circumstances. To introduce Gauss's law, we first need to introduce a concept called the electric flux. What is the electric flux? Well, to put it simply, the electric flux really simply counts the number of electric field lines passing through a certain region. For example, I have this piece of surface, and I notice that there are several electric field lines penetrating through it, and I count the number of field lines. What I get is what's called electric flux. But of course, in reality, electric field lines are not numerable. You cannot really count them 1, 2, 3, 4. This is just a figurative speech. Okay, so basically this is telling you how many field lines you can count. Basically, it really is telling you how strong the electric field is in this region and how they penetrate through the region. If you compare these examples, you take a look at these two. Okay, pretty much have the same surface, but here we have a stronger electric field distribution, so figuratively we say we got more field lines, we got denser distribution of field lines. So if you compare these two cases and you ask yourself, in which case is there a stronger electric flux, greater electric flux? Of course, that will be the second case. Okay, so the electric flux certainly depends on the strength of the electric field. The stronger the electric field, the greater the number of field lines will penetrate through this region. And secondly, if I compare those two cases, okay, again, the same area, but this time the electric field lines are pretty much parallel to the surface. Now, if that is the case, do they really penetrate the surface? No, they don't, right? They just, point along the surface. They don't really poke through it, and therefore, in this case, the flux will be pretty small. So therefore, if I want to define the electric flux, I want to consider several things. Okay, one is the size of this area. Secondly, the strength of the electric field. And thirdly, the orientation of the electric field lines, how they are oriented relative to the surface. Okay, in particular, if I look at a patch of flat surface, okay, the area of that surface is A. One can introduce a vector, this vector A, whose magnitude equals to the size, the area, whose direction is defined to be perpendicular to the surface. So you have this green vector A. Okay. Meanwhile, over this area, there is an electric field E pointing this way. Okay, we assume the electric field to be uniform throughout this area. which is always the case if I make the area small enough. Now E has a certain direction which just doesn't have to be the same as the orientation A. So there's an angle theta between them. Now my question is, how big is the flux going through the surface? Of course that depends on A, right? The area A. The greater the area, the greater the flux. It also depends on the strength E. The stronger the electric field, the greater the flux. But it also depends on the relative orientation between A and E. You know, if E points that way, which is parallel to the surface, in other words, perpendicular to the vector A, then now nothing will actually penetrate the surface, and therefore the flux will be zero, right? So when theta is 90 degrees, the flux is zero. On the other hand, for the most efficient penetration of electric field line through the surface, I want to reorient the electric field so that it is parallel to the area A, right? So everything goes right out. So therefore, when theta equals 0 degrees, you have the strongest flux. So I gotta multiply this by another factor, a function of theta, such that it is maximum when theta is 0 degrees and 0 when theta equals 90 degrees. Okay, so what do you think you can think of a function which is 0 at 90 degrees and at maximum at theta equal to 0? Well, obviously the easiest choice is cosine theta, right? So this is how we define the flux phi E, the electric flux through this surface. It is defined as A times E times cosine theta. Make sense? Okay, now I'm sure you recall, this really is just the dot product of A and E, or E and A. This is the definition of the electric flux. So how is that related to Gauss's law? Well, we're going to derive Gauss's law in just a little bit. But before we do that, let's first take a look at what's so good about Gauss's law. Why do we bother to rewrite Coulomb's law in this different version? All right. Gauss's law describes the behavior of this electric flux, which we just defined in the previous page. It says that the electric flux through a certain enclosed surface, okay, not a patch anymore, rather it's a self-enclosed surface with no holes on it, okay, such as this surface, that surface. The Gauss's law states that the electric flux through this enclosed surface has nothing to do, okay, in other words, it is independent of the shape and size of the net. By net, I mean this enclosed surface, which captures a certain amount of charge inside. In other words, we can choose whatever shape of this surface we like, as long as it encloses the same surface. We are going to obtain the same amount of electric flux. Now, why is this important? Because this allows us to choose whatever shape of the net we want. As long as it encloses the same surface, we're going to obtain the same amount of flux. And if we have a spherical symmetry, for example, then we might as well choose this particular net in the shape of what? A sphere, right? And if the symmetry of the problem is cylindrical, then we can reshape the Gaussian surface, or the net, so that it is shaped as a cylinder. In other words, we can exploit the symmetry of the problem based on our freedom of choosing any surface, any shape of the net we want. This is guaranteed by Gauss's law. Okay, so we're going to show that, and we can see how we can apply it to cases of high symmetry.